So the theory of compact groups is all about character, you know, what kind of fiber you're built from, you know, where is your upstandedness or lack thereof, but then also, regrettably, class, what class you belong to. That's a very 19th century or you know, currently it's a notion, not, never mind. So that was character, now what's class? I've said it before, but it should be repeated often. It has a very good intuitive thing about it. Just in this first non-abelian class we have studied, which is a triangle. You know, you can rotate a triangle, and that you can do in three ways. You can do nothing, that's called identity, rotate by 1/3, rotate by 2/3 of a full circle. So there's a class of rotations. And then there is flips. You can flip over z-axis, y-axis, well, the three axes, they're not the three symmetry axes of a triangle. So there are 6 elements, and they're divided in classes of rotations or flips. And of course, identity is always a class of itself. You know, the one that does nothing is a class. So the intuitive notion of this is that you take an operation, like operation B, and now you apply another operation in your symmetry group, let's call it Y. And that generally gives you a different operation. So for example, if B is a flip for a triangle and Y is rotation by 1/3, then this formula says, change your coordinates by rotating by 1/3, apply flip reflection element B, and then rotate back. And there is no reason why you should get the same operation when you do this for non-abelian groups. But what you'll get is something that flips, will be around different axes. So now, if we take a character, so what we do is we have a representation of this. So these are abstract elements. They are only defined by multiplication table. These are matrices in which I have a laboratory setup. If I take a character of this, I find by cyclic symmetry that character doesn't get changed. So what it says is that all elements which are related by conjugation, ugly word, but just means going into a different frame and coming back, they are of the same class, and this agrees with our intuitive notion because their flips will be one class and rotations will be one class. What I'm doing now will suffice to simplify this great orthogonality theorem, which is zillion indices, to very concrete, very simple, and very applicable small dimensional thing, which is called character orthogonality theorem. Oh, the great orthogonality theorem, indices are free, so I can decide to identify these two indices and sum over them because they're free. If I do that, I'll multiply these two Kronecker deltas because I'll identify, mu, and I sum over these two guys. If I sum over them, I'll get that mu equals nu. second time I do the sum, I'll get a dimension of the group because there'll be a canonical delta. And this guy is around for a ride anyhow, because, you know, I'm assuming that alpha equals beta by now, so same representation, so that's only one. So it's very easy to write this thing as a statement about characters. The only thing that's not clear is, have I lost some very important information, because there are lots of indices around and I'm getting rid of them. But if I sum over these, I get chi, character of this group. If I sum over these, I get character of inverse. Sum over group elements, chi alpha, group element, times chi. So this is just a number, it's not a matrix. This is abstract operation, but the way the character was defined is that I use representation to take the trace. Remember, character was defined, you take a matrix representation, sum upon diagonal for a given group element. So that's the first guy. The second guy is inverse. You're summing up elements. So you average here over all group elements. So H is dimension, order of the group, order. Matrices have dimensions. There was dimension here, but when you take a trace over this, this will cancel that. So we just get that this thing is 1 if it's the same representation, or 0 if it's not. So that's it, very simple. So why is this orthogonality? This guy here is array of H numbers. In other words, this is a vector. And I take the character of the first one, and let me forget the synthesis for a moment. It's irreducible. So first one, second one, to the last one. Instead of those crazy matrices, I just have, you know, H numbers where H is the order. And now, because of unitarity, R minus 1 means complex conjugate, and I can put R minus 1 on this side, so it's easier for me to draw it this way. And now it says the characters, complex conjugates of arranged this way. This is 1. In other words, characters create vector of unit length. So I really have character orthogonality theorem. So in some totally miraculous way, I went step by step, Schur's lemma, blah, 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 blah. Suddenly, I created for you a vector of the same, of dimensionality, which is the order of the group. And it's a unit vector, because if I multiply it by its transpose complex conjugate, I get 1. So that's much, much simpler than what we saw before. Now that turns out to be extremely useful. So there are two things to say about it. And in practice, you'll never see orthogonality, great orthogonality theorem again. You know, it was just a stepping stone in deriving the character orthogonality, but it turns out this is all we'll need, number one. You know, it's all that we'll need to produce irreducible representations of any finite group. Number two, these characters are actually quite simple numbers, and there are tricks how to compute them without writing matrices, you know, just by using character orthogonality, basically. That's the first remark to make about this. The other remark is that I have to remember what the class does. Class said that character for any group element in the same class is the same. So it means because my problem is divided into classes, it means that there are actually group of entries in this vector which are just the same. So the thing that you're formally summing over all group elements, but characters don't depend on an individual group element. They only depend on the class your group element belongs to. So really the sum is over the classes. So the other version, which is used more often of the same theorem, is a class and character. If I take the number of elements in the kth class, so K now runs not over group elements, but over classes, compute the character for each class. That just means if you compute it for any group element in the class, you have it, but then it's the same nk times number elements in the kth class. And this is just an integer. And you multiply this by same class, but you have to take a complex conjugate because now it's a class of inverses of this operation. And this funny thing is curly C. This is the compact thing to do. You average over the group, but you weight by number of elements in a class. This is really all we'll need. So now the situation will be that we have a finite group. We first divide it into classes. We compute the character for each class. And next thing we'll show is that the number of irreducible representations is the same as number of classes. But the transformation from one to the other is not obvious, but it's a unitary transformation, meaning that there'll be a matrix that goes from organizing your thing in terms of classes to organizing your thing in terms of irreducible representations. This is all very abstract. It's all correct. It's algebra. There's nothing to it. I will now have to, define a theorem. Another thing that could now happen is, I have my big matrix, which is my realization of, a frog jumping, flipping, or something. Mm-hmm. And the frog has a symmetry, so if I invert the frog, it's the same frog. But how do I know that I cannot do this in 7 different ways? I have these irreducible representations. So we have to prove that it's unique. So every time I have a representation, its decomposition to a reducible one is unique. There's only one way to do it. So that's the next theorem to do. And then we'll be ready to prove that the number of irreducible representation equals number of classes.
Professor, just before you go, can I just straighten up the notation? So
yeah.
The represented for the class and the C is the character?
Chi, the Greek letter chi is the character.
So what was the curly C then? Element?
What do you say?
What was the letter, the C, the curly C in the bracket?
Oh, the curly C stands for class. So every element has every group element belongs to an abstract class. And that class is defined by saying, if I run over all possible conjugacy, so let me go back to class because maybe I didn't emphasize it enough. So, if I take any group element and I go to, I perform a symmetry operation Y, and then I do my thing and go back, I usually get another group element. Now, if Y runs over the entire group or all possible symmetries, and I always find that A and B can be related, then A and B belong to the same class. For example, if B is identity, E or abstract identity operation do nothing, then Y times identity times Y minus 1, and this is true both of representations but it's true on abstract level, is identity. In other words, identity is always a class of its own. So one class is always the identity. The other ones, we can work them out for the 6 elements of the symmetries of the triangle. Sigma across x, one axis, sigma second axis, sigma three symmetry axis of triangle, they form a class. And that you check by multiplication. Rotating, it'll permute them if you use rotation elements. So Y is one of the rotations. It'll just permute the set, but leave it the same set. And if you flip them, you'll use a sigma square equals 1, and you'll get the same set again. So it's very easy to produce classes there on the abstract level, whereas characters are properties of representations. So every representation of a group element, every group element belongs to a class. And every representation of a group element gives you a character, which is evaluated in that representation.